And welcome to the video for Chapter 16 on the topic of heat transfer from Conceptual Physics, 12th edition by Hewitt. Alright, so we're going to talk about the three primary ways that heat is transferred. These are the big three: conduction, convection, and radiation. It's going to be the main focus of the chapter. Then we're also going to cover some auxiliary topics of Newton's law of cooling and global warming and the greenhouse effect. Okay? Alright, well, let's get to it. Okay, so heat transfers and changes of phase. Well, when do we expect it? Well, objects in thermal contact at different temperatures will reach equilibrium, and they'll do that in one of three ways or a combination of different ways: conduction, convection, and radiation. Those are the mechanisms for objects to reach equilibrium, because we spoke about before, heat will continue to flow until equilibrium is reached, which is just when an object and its surrounding are the same temperature, or when two objects that are touching are the same temperature. That's equilibrium, okay? All right, so let's start with the first, conduction. So conduction is the transfer of internal energy by electron and molecular collisions. So it's actual collisions of little particles. At the microscopic scale, it's things bumping together. So it requires direct contact, all right? It works especially for a solid. So conduction is usually associated with a solid. Gases and liquids can definitely conduct. They're just not very good at it because there's not as much bumping. Think about a gas. The molecules are further apart. They're less likely to collide together to pass on that energy. All right, so it's a domino effect. It's all about conservation of momentum. It's molecule bumping, molecule, and so on. Okay, in a solid where all the atoms and electrons are kind of locked together, it's primarily electrons that are doing the bumping, but the mechanism is the same. Okay, so conductors, right? Well, there's good conductors and bad conductors. Okay, well, a good conductor by definition conducts heat quickly. So substances with loosely held electrons are those that have good conductive abilities: silver, copper, and other solid metals. Now here, you might think, wait, are we talking about electricity? Because if you know anything about electricity, you probably know silver, copper, and metals are conductors of electricity. And you probably maybe even know that electrons are how electricity is propagated. Well, it turns out conducting heat and conducting electricity work very similarly, and a good conductor of heat is also a good conductor of electricity. Okay, they're physically different things. I mean, ultimately here we're talking about collisions and mechanical energy of the actual electrons that have to do with their inertia. When we talk about electricity, it is a fundamentally different property. It has to do with their magnetic field. So there's different physics at play, but regardless, good conductors of heat are good conductors of electricity. Okay. So poor conductors, those are the objects that don't transfer heat very quickly through direct contact, are also called insulators. These include solids that have molecules with tightly held electrons, right? So they vibrate in place, but they don't move around very much. All right, so they're good insulators, poor conductors. Glass, wool, wood, cork, some kinds of plastic foam for sure. Gases like air definitely are poor conductors. All right. And substances that trap air, since air is such a poor conductor, also work well as poor conductors, because then you have kind of the average heat conduction is low. Wool is a good example of that. So even though the wool fibers might be conducting heat, there's so much space between those fibers, so many trapped pockets of air, that the overall effect is poor conduction or insulation. Feathers work really well for that as well. All right. Even snow is a poor conductor. Okay. So if you hold one hand of a metal bar against a piece of ice, the end of your hand will soon become cold. Does cold flow from the ice to your hand? Is that what's happening? Right? Is that why you start to feel cold? Right? It sure seems like it, but of course not. Cold never flows. Cold cannot flow. It's heat flowing from your hand, which triggers nerves in your hand to start sending signals to your brain that your hand is cold. Okay? But it's heat flowing from your hand. All right. So insulation. Right? Well, we're talking about conduction, so I talked about insulators like, feathers, for example, or plastic foam. So what do we need to know about insulation? Well, it doesn't prevent the flow of internal energy. It will never completely stop it. There's no 100% insulator. It doesn't exist. It can slow it down dramatically, but it doesn't prevent it. Okay? So we can slow down that rate. For example, insulation in walls like rock wool or fiberglass slows the transfer of internal energy, which means that it basically just takes longer for your house to reach equilibrium with outdoors. It will eventually reach it. You still have to, maintain that difference between your house temperature and the outdoor temperature. But since it's going at a slower rate, that means that that you have to use less power to maintain it. And that's the whole goal. Not zero power, just less power. All right. Also, the idea of insulation works well for walking across hot coals. All right. So, dramatic example: walking barefoot, like this guy here, across burning hot coals can work because the coals are a poor conductor. All right. All right, so that's number one, conduction, direct contact between molecules or atoms or electrons. But what about convection? Now, convection is probably the most wishy-washy in terms of the way we're going to approach it of the three transfer methods of heat, because it kind of involves the most complicated ideas, but it has to do with the bulk movement of fluids, all right? The bulk motion of fluids. And that rather technical expression means that we have big pockets of fluid that are moving relative to the overall body of fluid. Kind of like in this picture, right? We could imagine pockets of fluid that are rising up, other pockets of fluid that are being pushed down, cooler ones that are sinking. If you've ever seen, these circular structures, that's convection, right? Sometimes they're called convection cells, each circular structure, okay? And, so like a roiling boil, anything like that is an example of convection, okay? So what drives convection? Well, the reason is that warm air rises. The warm air expands, it becomes less dense, and is buoyed upwards because now it is essentially like a balloon relative to the rest of the surrounding gas around it. Now, of course, it does disperse with that gas, so it's not exactly like a balloon, but it doesn't disperse at a faster rate than it rises. So it rises with its lower density, higher energy state. But what happens is eventually it rises until its density equals the surrounding air. How is that possible? Well, because the air decreases of density as a function of altitude, because there's less and less gravitational push on the atmosphere as you go up. And it's rather dramatic, so hot air doesn't have to rise all that far before it reaches low density air up in the upper atmosphere and is then able to sink back down. For example, smoke from a fire rises and blends with the surrounding cool air. All right? So that expansion, that rising expansion and that rising is a cooling process. It's a way to dissipate energy. All right? It's opposite to the warming that occurs when air is compressed. If you compress air, then you have warmed it up. Okay? And here we have the cloudy region behind or above a pressure steamer or a pressure cooker, and that cloud has expanded so much that it's not nearly as hot as the hot gas coming directly out. So the invisible part is very hot, would burn you, but once it's already expanded and started to phase change, then you, because there's a little suspended liquid droplets now in the air, which you can visibly see, and now at that point it's much cooler and it is safe to touch. All right. So although warm air rises, why are mountaintops cold and snow covered while the valleys below are relatively warm and green? Right? Because that's a valid question. We're talking about all this warm air rising. Doesn't it mean like that warm air should rise up and maybe, brush across the tops of mountains and, so there shouldn't be warm breezes up there? Well, what do you think? Okay, not so, right? So our answer is here. The warm air cools when it rises, so it's not warm anymore once it gets up there. And more so, there's a thick insulating blanket of air above the valleys, right? So what keeps them warm is the fact that there is essentially an insulation over those valleys due to their shape, okay? All right, so convection continued. And this is a rather neat one because this is going to relate back to the high specific heat of water. All right, so let's talk about winds. So winds are the result of an uneven heating of the air near the ground. All right, so that some parts of the ground might heat up more easily than others, and then that's going to force air to move around. A good example of that is comparing ground to water and a sea breeze. So the ground warms more than water in the daytime. The warm air close to the ground rises and is replaced by cool air from above the water. All right, so that is an example, right? We can see it right there. We can see that during the day, the ground is heating up more easily than the water because the ground has a lower specific heat than the water. So for example, has a temperature of 70 degrees after a few hours of direct sunlight, whereas the water only has a surface temperature of 65. That makes the air warmer here. This air is forced upwards, but then it has to go somewhere after it goes up into the upper atmosphere and cools. And so it's going to sink back down to where it can, over the water. That's going to create an overall effect of a breeze coming off of the water during the day. All right. Okay, so continuing on with the third and final mechanism of heat transfer called radiation. All right, so radiation is fascinating, and it's also the tip of an iceberg of a much bigger topic, which is light, which we'll spend quite a few chapters on later. But here we're talking about it not because we want to jump ahead and talk about light. We'll have time for that later in the semester, but instead because it is a valid means of heat transfer. So what is it? Well, it's a transfer of energy from the sun through empty space. For example, it's also the transfer of any energy via electromagnetic radiation. So radio waves are a form of electromagnetic radiation. Infrared waves, like they're coming off of this fireplace, which are just a little bit beyond the visible spectrum, a little bit lower energy than red. That's why we call it infrared. And then visible light coming off of a light bulb. Okay? These are all examples of transferring energy via electromagnetic waves via what's called radiation. All of these are radiating waves, light waves, also known as electromagnetic waves. Okay? So the surface of Earth loses energy to outer space mostly due to what? What do you think is the best answer here? How would we lose energy in outer space? We're conducting with space? Is there any fluid in space? Of course not. It's got to be radiation, which makes sense because it's the topic that we've just started covering. All right? So, which body glows with electromagnetic waves? The sun or the Earth? Okay? That's easy, right? It's got to be the sun. No, it's both. The Earth, just like any basically, kind of object that isn't going really hot, is glowing at lower temperatures, and the color that corresponds to that lower temperature isn't visible to the human eye and would fall in the infrared spectrum. All right? So Earth is indeed glowing in the infrared. So are you. So are most objects. The very, very coolest objects can glow in the microwave spectrum, but it has to be very, very cold. All right? So radiant energy is transferred energy. It exists as electromagnetic waves, so it's called EM waves. They can range from the long radio waves, right? And a microwave is a type of a radio wave. It's the shortest of the radio waves, or the least long of them. And then all the way up to X-rays. So if something's really hot, if it's millions of Kelvin, like the center of a star, or an exploding star for that matter, then it can actually release heat in the form of X-rays, okay? In the visible region, ranges from long, red, which is the coolest, to the hottest, violet, okay? So the wavelength of radiation is related to the frequency of the vibration. And this has to do with the fact that the speed of light is a fixed value. Again, more on that later. But there's a direct relationship between wavelength and frequency. And simply put, low frequency vibrations produce long wavelength waves, all right? So if it's slow, right, if this movement is slow, then the wavelength is long, right? So we see a long wavelength. On the other hand, if it's really fast, right, if it's going up and down really fast, then the wavelength is much shorter, okay? So high frequency, shorter wavelength. If one goes up, the other must go down. I have a big frequency, a big numerical value, then my numerical value for wavelength must be small, okay? Because they always equal the same. So thus they must balance out, all right? So how do you create radiation, and how does that transfer heat? Well, the emission of radiant energy takes a few forms. Every object above zero radiates, okay? Because what happens on the fundamental level is there's always electrons, they're always moving. As they move, they accelerate. As they accelerate, they create a changing magnetic field, and that changing magnetic field creates a changing electric field, and thus light is born. Now that's getting ahead of ourselves a little bit, but the point is that every single object, whether it's a gas or a solid or a liquid, radiates light. It's fascinating, really, all right? Now, again, we don't really think of that necessarily because a lot of that light is invisible to the human eye, but everything is making light. Now, you might say, well, but I see things, is that I see the wall, but it's not like the wall is emitting light like a light bulb or the sun, because the color you see on the wall is reflected light. That's not emission, that's reflection, which is a whole topic in itself. And that's more like heat bouncing around than being created, okay? So from the sun's surface comes light, called electromagnetic radiation or solar radiation. Okay, it's a source of energy. From the Earth's surface comes terrestrial radiation in the form of infrared waves. Much of that is reflected, although the Earth does produce its own heat, largely through radioactive decay. Okay? So there's a direct relationship between frequency of light, thus color, and temperature, right? A direct proportionality. The frequency of radiation is proportional to the absolute temperature of the source, and frequency is color. For example, if a source has a temperature of 3200 Kelvin, then that corresponds to a frequency that is blue light. On the other hand, if a source has a temperature of 2400 Kelvin, then that's going to correspond to a frequency that shows up to the human eye as green light, okay? Well, it's green light and it happens to be something we can see, thus we call it green. And 1600 red, okay? Now, when you heat things up, those things that can be heated up so much, they start to glow hot. They usually glow red hot. That's because their peak wavelength is going to be in the infrared, and you're usually seeing the tail. So you can imagine a peak wavelength like this, which is in the infrared. And what you're seeing then, what you're viewing is that piece of metal is glowing red hot, think like holding a fork above the stove. As that glowing fork is glowing red, you're seeing this, maybe this is the human vision here, in this range right here, then you're seeing the tail end of that curve of light, that radiated light, that emitted light from the glowing object. You're seeing the tail of it in the red, even though the peak is well within the infrared. The reason I bring that up is because we don't see many things that say glow, blue. That's because almost everything will melt, go through a phase change before it reaches a temperature where the peak wavelength actually would correspond to blue. The exceptions are some stars, and certain metals can get up to the point where they glow green. They don't actually appear green because when something's glowing green, there's just as much of the red, orange, and yellow as there is of the blue, indigo, and violet, because the rainbow is ROYGBIV, which is red, orange, yellow, green, blue, indigo, violet. And if you're right on the green, then you got just as much on symmetric on either side of that. Think the colors in the rainbow. And so the overall effect to the eye is white, right? Because it's an overlay of all those colors that you're actually observing. So if something's glowing, quote unquote, green, it appears white. I bring that up again because certain metals like tungsten will not melt, and you can heat them up so much that they actually will stop glowing red and start glowing white. But that's very rare, right? Really neat, but very rare. All right? So the range of temperatures of radiating objects, well, room temperature emission is definitely in the infrared. That's like, humans and walls and windows and, there's so many things that are going to glow in the infrared. The temperatures above 500 red light emitted along this visible wavelength. You can start to get yellow light emitted when you're above 600, and then finally you can get into the white light at about 1500. Okay? So, absorption of radiant energy occurs with emission of radiant energy. So, in other words, things that are good emitters are also good absorbers. So, the effects of surface of material on the radiant energy. So, any material that absorbs more than it emits is a net absorber. Any material that emits more than absorbs is a net emitter. And we're still talking about radiation here. And net absorption or emission is relative to the temperature of the surroundings, not to the properties of the material. Because again, something that is a good emitter is also a good absorber. Okay? And so further on, the absorption of radiant energy occurs along with emission of radiant energy. Right? So as I said, right? Good absorber, good emitter. Poor absorber is also a poor emitter. So let's talk about some examples. A radio dish antenna is a good emitter. It is also a good receiver. Okay? All right? If a good absorber of radiant energy were a poor emitter, its temperature compared with surroundings would be what? Well, it doesn't work. It'd be higher. And it could never reach equilibrium with its surroundings. Thus, it's impossible. A hot pizza placed in the snow is a net, right? So now think about the relative temperature, right? So the pizza is going to start, emitting more than it's absorbing because it's going to try to reach equilibrium with the snow. And so overall, even though it's still going to be absorbing energy from the snow, it's not going to be absorbing nearly as much as it's emitting. So which melts faster in sunshine, dirty snow or clean snow? So this has to do with the properties that lead to good absorption or emission. It turns out that darker objects are better emitters and absorbers. So which is going to be dirty snow, all right? Because it absorbs more sunlight. Black is the color that both emits the most and absorbs the most, all right? Reflection of radiant energy is the opposite of absorption or emission. It's a different process altogether. Any surface that reflects very little or no radiant energy looks dark, all right? So examples of dark objects, eye pupils, open ends of pipes in a stack, open doorways, or windows of a distant house in the daytime. So reflection, we can think of it like this, right? Basically a hole where the light just isn't coming back out, it's trapped inside. So darkness often due to reflection of light back and forth many times, partially absorbed with each reflection, okay? And again, a reminder, good reflectors are poor absorbers. So which is the better statement? A black object absorbs energy well, an object that absorbs energy well is black. Both say the same thing, so both are equivalent. What do you think? It's an object that absorbs energy well is black, all right? Not the other way around. This is the cause and effect question. The color black doesn't draw in and absorb energy. The color black is there. That color exists because of the physical process, right? And that's pretty cool because we take colors as granted. We take colors as just kind of a natural state of the world around us, but they're not. Colors are a consequence of the natural state of the world around us, all right? And that's a cool thing about physics is when you start to be able to think about things like that. Okay, so now on to our final two auxiliary topics, Newton's law of cooling and the greenhouse effect. All right, so let's move right through these. Newton's law of cooling. Well, it tells us that there's an approximate proportionality to the temperature difference delta T between the object and its surroundings. In short, the rate of cooling is proportional to the difference in temperature. All right, so if you're twice as hot as your surroundings, then you're going to cool twice as fast than if you're, that like, so let's say if my temperature difference with my surroundings is 5 and your temperature difference with your surroundings is 10. Well, that means you're going to cool off twice as fast as me. Okay? So examples, hot apple pies cool more each minute in a freezer than if left on the kitchen table, and then warmer houses leak more internal energy to the outside than a house that is less warm. All right? So that means it's much more energetically demanding to keep a bigger delta T with your surroundings. Okay? Definitely. So Newton's laws of cooling applies to rates of warming as well. So objects cooler than their surroundings warm up at a rate proportional to delta T. For example, frozen food will warm faster in a warm room than in a cold room. Okay, so that's you can cool off a drink, a soda, faster in the refrigerator than just leaving it sitting in the room. Okay, all right. It is commonly thought that a can of beverage will cool faster in the coldest place of the refrigerator. Knowledge of Newton's law of cooling definitely supports that. Okay, this isn't one of those gotcha moments. It's common sense ends up being the correct one here. Okay, so finally the greenhouse effect. Well, it's named for its similarity to the temperature rising effects in a florist's greenhouse. How so? Well, it's actually a pretty neat idea and hopefully a simple one. The idea is glass is transparent, and transparency, by the way, is an emission process. Well, we'll talk about this more in our light chapters. But being transparent to a particular wavelength of light means that wavelength of light can pass through the material. Okay, and so this short wavelength of radiation from the sun is transmitted. So what do we mean by short? Well, the visible spectrum. That's all the red, the orange, the yellow, the green, the blue, the indigo, the violet, all the colors of the rainbow. They're relatively short. Okay, so that means they're high frequency, short wavelength. Okay, visible light passes through glass. Why is that? This happens to be a property of glass, which is why it's so popular, because we like to see the colors that we've evolved to see, right? So anyway, so glass has that property, lets visible light pass through. But here's the thing. The objects in the greenhouse, they warm up, the molecules in those objects vibrate. As they vibrate, they emit infrared light. Just like you're emitting infrared light. You're an emission source of infrared light, okay? Which is, again, a form of heat, not to lose track that we are, after all, talking about heat here. Right? So then that heat then is being radiated away, for example, from this smiling flower. But that's the thing. Glass is opaque to long wavelengths like infrared. So that means that all the infrared gets trapped. Well, that's interesting, because now we have energy continuing to come in, but not as much energy getting out. Now, can some energy still get out? Well, sure, because the glass itself can heat up. As the glass heats up, it can conduct with the air, right? It can cause convection off of the surface. Right, so there's still slowly an energy flow, but the opacity of the glass to the long wavelength light is creating a real deficit in terms of the energy flow out, right? Which is good. I mean, I don't want to make it sounding negative. You actually want that. You want more energy coming in than going out, because your greenhouse can get hotter and hotter. Now, of course, as the greenhouse gets hot enough, then it can kind of reach a state where it won't continue to get hot, because then it's the energies that are going to find those ways through conduction and convection to start flowing out at that faster rate. Just think Newton's law of cooling, okay? But it still allows it to heat up in the first place. The greenhouse then, as long as the sun is shining, will maintain a hotter temperature than its surroundings, okay? All right, all due to this being, transmissive to certain wavelengths and not transmissive to others. Okay, well, it turns out that also works for atmospheres of planets. So understanding the greenhouse effect requires the two concepts. All things radiate at a frequency, all right, that depend on the temperature of the emitted object. That's why the flower radiates at a frequency that is lower frequency, longer wavelength than visible light, okay, because it's a lower temperature than the sun, certainly. The transparency of things depends on the wavelength of radiation, okay? So excessive warming of a car's interior when the windows are closed on a hot sunny day. The sun's rays are very short, pass through the car's windows. The absorption of the sun's energy warms up the car interior. The seat, the dashboard, they all start emitting that longer wavelength infrared. The car interior radiates its own waves, which are longer, but they don't transmit to the windows. The car's radiated energy remains inside, making the car interior very warm, much warmer than the outside air. All right? And I always think of this, especially on a sunny winter day, where the air is really, really cold outside, but it can be very warm inside the car. And that's all due to the greenhouse effect. Okay, so how does it apply to planets? Well, it can cause global warming, okay? Now, some global warming is obviously good. We want to have a lower temperature or a higher temperature than we'd have without an atmosphere. That's life-sustaining. But it can also be a runaway greenhouse effect, okay? So the energy absorbed from the sun, part of it is re-radiated by the Earth as long wavelength terrestrial radiation, all right? That's shown here, all right? And then that terrestrial radiation is absorbed by the atmospheric gases and re-emitted as long wavelength terrestrial radiation back to Earth. So it's just bouncing around inside the atmosphere, not going back out into space. The radiated energy is unable to escape. So the warming of the Earth occurs. And notice that we mentioned these particular gases, these atmospheric gases. So there's certain gases that play a key role in absorbing that long wavelength and re-emitting it. H2O is a big one, so water in the atmosphere. Ozone is a really big one, okay? Carbon dioxide is another. So long-term effects on the climate are a present concern. So the greenhouse gases that contribute to global warming absorb, okay, your options, more infrared radiation than visible. That's the whole point, because that's the type of radiation that's being emitted by the surface of the Earth, the rocks, the valleys, even the ocean, and that's what that needs to get bounced around, okay? So more energy from the sun hits Earth in 1 hour than all of the energy consumed by humans in an entire year. Just to give you an idea of the sheer volume of energy that comes from the sun. It's amazing. Okay, so there you have it. The 3 big ways of heat transfer: conduction, convection, and radiation. We obviously talked a lot about radiation because it's the most complex. There's obviously the most ideas to understand there. Take note of that. We also talked about Newton's law of cooling and a bit about how the greenhouse effect works. I hope this lecture was interesting and look forward to more heat content next week.